Good afternoon, everybody. Let's get started with the class. So for announcements, homework 4 is due this Friday, so take a look at that on Canvas. Lab 5 should be in progress right now. We're going to start Lab 6 this week, and that's going to be on testbed system sensors. So last Friday's lab was a lot of tweaking software, changing gain in software in the control loop. And so you're going to go back to hardware this week and build some more electronics hardware and put some sensors on the board. Exam solutions are posted, so take a look at those. If you have any questions, stop by office hours. Grades are also posted, so stop by office hours if you have questions about grades as well. So during the previous class, we started MOSFET power dissipation. We're going to talk more about that today. We're going to talk about electrical power impacts on mechanical engineering. So we're going to tie electrical engineering and mechanical engineering, some thermal engineering concepts together. We're going to do some basic thermal analysis and talk about, to wrap up MOSFETs, some design considerations that you've touched in lab, but we're going to talk a little bit more about that. I think those are useful topics. And then if time, we're going to start DC conversion, DC voltage conversion and voltage regulation. Okay, so that's coming up. All right, so let's get back to, let's see here, my slide. Electrical power impacts on mechanical design. So, right, you're mostly mechanical engineers. You're learning about MOSFETs at this point. And so some of these design selections when electrical engineers or you are when you're designing MOSFET circuits impact the mechanical design and the thermal design. Okay, so that's why it's useful knowing some of these more detailed topics because they can affect your life and your work. So mechanical engineers are often responsible for the packaging of a product, and this includes the cooling approaches. You have to get the heat out. So if you have a voltage and a current flowing, you're going to have heat generated, and oftentimes not all the power, not all the energy goes toward the intended purpose. It goes to generating heat, which reduces the efficiency. And if the temperature gets too hot in some of these devices, you can damage the devices. This is where mechanical engineers come in to get the heat out through the package or otherwise. So the approaches to getting the heat out include heat sinks like these up here, right? So these are heat sinks, forced air, which includes fans, liquid cooling. Liquid cooling could be water, it could be ethylene glycol in water, that's antifreeze, PAO, polyalpha olefin, which is an oil used for cooling, or even fuel sometimes flows through electronics in certain platforms to cool the electronics. And also heat pipes. Okay, so these are heat sinks. This is the kind of heat sink that would attach to the package of the MOSFET that you're using. So you could attach your MOSFET to this. It gives you some fins here. Here's a typical heat sink for a chip on a circuit board. The chip's under this heat sink. It has some protruding fins on it. Here's another larger heat sink, right? Meant to transfer energy, transfer heat from the heat sink fins to the air. Okay, and then if passive cooling doesn't work, you can use forced air. So here's a fan. Typically computers over their processors and other chips have fans like this. Here's a single board computer. I think this is a Raspberry Pi with forced air. So on top, I think this is also a Raspberry Pi with passive cooling with the heat sink. Here's forced air. If you're doing that much processing that you need it. Let's see what else. And cold plates. Okay, so cold plates can have liquid flowing through them to try to maintain a constant temperature or limit the rise of temperature of that plate. And heat pipes have different materials inside to try to get the heat transferred from one place to another more efficiently than just a metal rod. So You can look at those. There's different technologies there. But these all fall in the domain of mechanical engineers, typically, to get the heat out. And the cooling approach affects meeting what we call SWAP C, size, weight, power, and cost. So if you ever hear SWAP, size, weight, and power, some people tack on C, size, weight, power, and cost. Some people say SWAP C squared, size, weight, power, cost, and cooling. Okay, so the cooling approach affects this. So if you just have a low power circuit board and you don't need any kind of heat sink, then that's probably the minimum volume consumed, the minimum size. But then as you start adding cold plates or heat pipes or fans, then you start adding size. If you start adding fans, now you've got to supply DC power, usually to the fans. So that increases the power consumption by the device, kill your battery faster. Okay, and all of these increase the cost of the product. So it's important to select the cooling approach based on the requirements, but also based on the objectives of the product in terms of SWAP C. So high power circuits include power supplies, power control devices like MOSFETs, and BJTs, transistors, amplifiers, audio amplifiers, RF amplifiers, often cause thermal challenges because those are generally higher power circuits. Okay, also circuits that do a lot of processing, FPGAs and some microprocessors require a lot of power. Some of the smaller microcontrollers are not such an issue, like you're using the Arduino board. Cooling isn't such an issue there, but once you get up to high processing power on more powerful microcontrollers and microprocessors, cooling becomes an issue. And these challenges span across engineering disciplines. So not only electrical engineers and mechanical engineers, as I mentioned, but thermal engineers to do the analysis, materials and processes engineers to figure out what materials should be used, what can you use in the product based on the requirements. So the electrical design selections affect all these disciplines and the work that is done under them. Okay. With that in mind, let's take a look at analyzing temperatures for a semiconductor device. Okay, often semiconductor devices specify a maximum junction temperature. And the junction is actually the source of heat within the device. So that's going to be the hottest part of the device and an important part of the device. So you don't want to exceed a maximum temperature of that junction. So think diode with a PN junction. Think the junctions within a transistor or a MOSFET. Okay, that's where the heat is generated because you have a current flowing and there's a voltage there, P equals I times V. You're going to have heat generated. Okay, so exceeding this maximum junction temperature inside the device will likely damage the device, or at least degrade performance. If it's an amplifier, the gain might change. If it's a microprocessor, you might get some errors. You might actually have some processors limit their rates, limit the processing based on things like temperature inside. So you could degrade performance or damage a device if you exceed those maximum temperatures. And so there's, for a first cut, heat flow and temperatures for these devices can be modeled using thermal resistance. Okay, so I like to draw a resistor and pretend it's a thermal resistance, and then I can treat this heat flow problem like it's an Ohm's law problem. Okay, and so data sheets often provide thermal resistance values. So we'll talk more about these, but in the upper right here, really small, you have these different R values and often R sub theta. And then there's junction to case, case to heat sink, junction to ambient. We'll talk about those. So let's say just for a component, like the MOSFET you have in lab, as current flows through it, there's some voltage across that device, it's going to heat up a bit. And so here's a view inside a transistor, like a MOSFET. And so let's suppose you want to transfer heat from the MOSFET to just the ambient air without any kind of heat sink or liquid cooling or anything like that. Okay, so electrical power goes into this device that causes heat. That heat has to flow somewhere to ambient air. And if it has nowhere to flow, this device is going to keep heating up itself until it destroys itself. So you have this junction temperature T sub J. So that's right there. And then you have an ambient temperature, let's say it's room temperature, which is cooler than inside that device. And you have to get that heat flow to happen. And let's model that. We're going to model that like this. So we're using a thermal resistance, R sub theta JA, that's junction to ambient resistance. So you have heat flow, the electrical power comes in, causes heat. There's some temperature, T sub J, that's the junction temperature. And then the ambient temperature, which is, well, needs to be cooler than the junction temperature if this cooling is doing what you want it to do. So that's how we're modeling heat flow using a resistance as well as the temperatures. So here's the diagram of that. So here's a thermal resistance, R sub theta, and there's heat flowing. I'm calling heat Q here. Later, I'm going to use the variable P for power because Q is heat flow. It's in watts. And Q, we use Q for charge in electrical engineering. So I'm going to start using P in a minute. But they're power values in watts. So you have a certain amount of heat flowing here. And delta T is a temperature difference on either side, from one side to the other of that thermal resistance. That's just like a voltage difference across a resistor. And R sub theta is this thermal resistance. So Q is in watts. The temperature difference is Celsius minus Celsius, which is Celsius here. And you have the thermal resistance. And if you work out the units for this Ohm's law-like equation, it's degrees C per watt. So delta T equals Q times R sub theta. And just think of that like Ohm's law. If you can visualize current flowing through a resistor and a voltage being caused across that resistor, then visualize this the same way. In fact, some people go the opposite way when they're more comfortable with heat flow and thermal resistance and temperature differences. They think about Ohm's law in electrical engineering as if it were heat flow. Okay, so here's the model. You have T2 and T1, so temperature T2, temperature T1, and we have this, again, power in watts, this heat flow flowing through that thermal resistance. So T2 is going to be a higher temperature than T1. It's going to be that power times the thermal resistance. Okay, so that's a simple example with a single resistance value. If you had a device and you have air and you want to figure out the device's junction temperature, you usually know the ambient air temperature. You can look up the thermal resistance in the data sheet. And so you have air temperature, you have heat flow, you know what electrical power is going into the device, and you have the specified thermal resistance so you can get a swag of T2. Okay, before you go and do some more detailed thermal analysis with modeling tools. Okay, a little more complex example is an air-cooled heat sink like this. So you have a junction inside the device. That heat conducts to the case of the device. That case might be connected to a heat sink, and that heat sink gets rid of its heat into the ambient air. Right? So you have 4 different temperatures here: junction, case, heat sink, ambient. Okay, so you have this flow of heat from inside to outside to the air. Okay, and we can model the thermal resistances. These are usually specified between these temperatures. So here is theta JC, that's junction to case thermal resistance, right? And then you go from case to the heat sink. Here's theta C sub S, theta sub, no wait, R sub theta CS. And then you have from heat sink to ambient air. We'll talk more in detail about this. Okay, but this heat sink can also be a liquid cooled cold plate. It can be an air cooled chassis. So instead of connecting to a separate heat sink inside a box, you might connect to the box itself and let maybe a metal box get warm and dissipate heat to the outside ambient air. It could be a thermal mass. So if this device turns on a high power function only every once in a while, you might have some kind of thermal mass, piece of metal, different types of material that that absorb for a limited amount of time that heat, and then when the device turns off, that heat slowly gets dissipated. That's good for low duty cycle power applications. Okay, but you could still model everything I talked about there with thermal resistance, again, to get a starting point on a temperature analysis, a thermal analysis. So let's take a look at, well, the case you have in lab. You're operating a MOSFET without a heat sink. And we really didn't put much thought into connecting that MOSFET to something that would cool it, because you are dealing with fairly low current, less than an amp often in your lab. But the question here is, what is the maximum drain current that this MOSFET can control without a heatsink? Right? And I mean by can control without damage. So let's suppose you're controlling a voltage, you're controlling a current using a control voltage from a 5-volt microcontroller, and you're applying that control voltage directly to the MOSFET gate. So the gate to source voltage is 5 volts. And then you're going to allow the current to be on for a long period of time, right? Let's suppose you're running your motor at full speed, 100% duty cycle, and you're going to leave it on. And the ambient temperature is 25 C. Okay, so those are the conditions. And if you look into the data sheet of this MOSFET, you'll see T sub J, the operating junction temperature and the storage temperature range, is -55 to +175 C. Okay, there's also a soldering temperature here too. Okay, and then some thermal resistance values are given. So junction to case resistance, 1.5 degrees C per watt. Case to sink with a flat surface and with thermal grease on it, right? There are these conditions. 0.5 degrees C per watt typical. And then there's a junction to ambient. Okay, so those are the 3 values that are given in the data sheet. So we're looking at this case. We have this dissipated electrical power heat through a thermal resistance. There's nothing connected to this case, so we care about the junction to ambient. So here's TJ, junction temperature. Here's TA, ambient temperature. And then that heat goes out into the environment. So let's determine the maximum dissipated power without exceeding the maximum junction temperature. So here's how you calculate the junction temperature. T sub J is the ambient temperature. We have that. We want to figure out this p-value, and we have the junction to ambient thermal resistance. This feels just like an Ohm's law problem. Okay, so we can solve for P. This is the maximum dissipated power. T sub J minus TA over R theta JA. So if you put those numbers in there, the maximum junction temperature, 175. Ambient temperature, 25. R theta JA, 62 degrees C per watt. You get 2.42 watts. That's not a whole lot of power, right? I mean, we work with light bulbs that are tens of watts, and but this is just to give you an idea of that power dissipation. But the dissipated power without exceeding the maximum junction temperature when that power is dissipated by the MOSFET cannot exceed 2.4 watts. Let's look at what current that is. So determine the current ID based on this max power value to find out how much current can we control without a heatsink. So we're using VGS of 5 volts, that's the microcontroller voltage. We talked during the last class about RDS on, that's the drain to source resistance when the MOSFET is turned on with the 5 volt control voltage. We had 66.7 milliohms. So you can figure out the power dissipated, I squared D, ID squared, times RDS on. So I squared R, solve for ID, and put those values in there, 2.42 watts, 67 milliohms, you get 6 amps, right? So you can't control more than 6 amps of current without a heat sink, some way to get the heat out of this package of this MOSFET. And 6 amps, that's a reasonable current, right? The MOSFET's going to be really hot. I wouldn't touch it. If putting 5.5 amps for a long time, that MOSFET's going to get hot. But we know from the characteristic curves that we talked about that these MOSFETs can handle tens of amps, right? Well, when you get the heat out. So R theta JA is specified under specific conditions. So you got to read the fine print of the data sheet. There's a certain mounting and certain PCB characteristics that are specified to make sure you're getting this 62 degrees C per watt. So you got to read the fine print there. So I would say that using the specified junction to ambient resistance is a rough estimate. I would go into a more thorough analysis and or test to make sure we're not exceeding the temperatures we expect from the model. Okay, so you can use this approach though as a simple thermal analysis for starting a design and then perform testing, especially if you're approaching the device temperature limit. So in lab, you could do the analysis, you'd find out how much you're dissipating, and you'd have so much margin that I would say we're good. But if you're starting to approach, your model says, oh, we're at 165 degrees C, you might want to take a look at a more detailed analysis or test at lower powers to make sure the model you're using is working compared to measurements. Okay, so that's a MOSFET without a heat sink, and I'm showing you the limitations here. Let's talk about using a MOSFET with a heat sink. So we're going to use the same device, the same MOSFET. And let's say you want to control 10 amps. You have some solenoid, some motor, some heater, some circuit board that requires 10 amps. And you're operating in an air temperature, roughly room temperature, 25 C. And so you want to know this heat sink that you found online, will this heat sink work using natural convection, no forced air? And the real question is, will the junction temperature using this heat sink exceed 175 C? So let's just use the I call it Ohm's law model here. So we have this dissipated electrical power in, a junction temperature, case temperature, heat sink temperature, and then ambient, the air temperature. And all of these thermal resistances in between, junction to case, case to sink, sink to ambient. And again, we're going to consider realistic data. These are the same thermal resistances that we used on the last slide. But let's look at some heat sink data. So this is out of this particular heat sinks data sheet. What this manufacturer specifies, instead of thermal resistance, is heat sink temperature rise above ambient for different power dissipation values, right? So 0 watts, here's 0 watts. There's going to be no rise above ambient. You try to dissipate 1 watt into this heat sink, Okay, and so you get this delta T value. So with natural convection, the temperature is going to rise about, so 15.97, that's very precise, about 16 degrees C. So 1 watt into that heat sink, this delta T is THS, T heat sink in this case, minus TA. Okay, so that's temperature rise. Now you'll notice with 200 linear feet per minute airflow, 400 linear feet per minute airflow, you get much lower resistances, but let's concentrate on natural convection. You don't want to have a fan in this case. Okay, so you can see as you put more power in, you have a higher temperature difference, right? Here at 9 amps, there's going to be 100 degrees C temperature difference between the heat sink and ambient. Natural convection, or 9 watts there, okay? So for 9 watts, over 100 degrees temperature difference using that heat sink. But also notice that the thermal resistance is not linear with the heat flow using natural convection. Right? So this is about 16 degrees C per watt. This is about 8 degrees C per watt if you calculate delta T over delta P. So just calculate the resistance. So the resistance, thermal resistance isn't constant for this heat sink and natural convection. It changes. So that's why probably this manufacturer gives this kind of table instead of a range of resistance values based on power input, because that wouldn't make sense. Ohm's law is linear. This is not a linear relationship. Okay, so you're going to calculate the dissipated power to select the specific temperature rise. So let's do that. So let's calculate the power for ID equals 10 amps. You have this 10 amp device you're controlling with this MOSFET connected to this heat sink. Power is I squared R. So you have I squared D, ID squared, RDS on. That's the power. So here, 10 squared times 0.067, 67 milliohms is 6.7 watts. Okay. And let's determine now the heatsink temperature rise. So delta TSA, right, from sink to ambient, is TS minus TA. And for 6.7 watts, let's call that 7 watts. If you look down here in the table, natural convection, 7 watts, 90 degrees temperature rise. Sink, between sink and ambient. Okay, so to determine the junction temperature with the heat sink attached, add all the temperature rises to the ambient temperature. The ambient is 25 C. Let's add all the temperature rises across sink to ambient, case to sink, junction to case. Okay, so you get this here. So the junction temperatures, TA, ambient temperature, plus the difference between sink and ambient, plus, now here's the, what I call Ohm's law equation. We have the power dissipated by the heat sink times the thermal resistance, right? Because that power is flowing through this case to sink resistance. And then that power also times the junction to case resistance to get TJ. So that's 25 plus 90, right? So there's 25, 90 is from the table here. 6.7 times 0.5, that's the power we calculated up top for ID equals 10 amps, right? Times 0.5, where did I get the 0.5? That's this R theta CS, case to sink, flat, greased surface, 0.5. I'm using the typical value here. And then 6.7 times 1.5, this is the junction to case thermal resistance. And so you get 128.4 degrees C. Okay, so this junction temperature is less than 175, less than the maximum junction temperature allowed for this device. So the heatsink will work, even natural convection, without a fan. Okay, and notice that the air interface dominates. Look at the factors here. You have these deltas, 90, 3.35, 10.05. That sink to air temperature difference is what's dominating here. It's not the device thermal resistance itself. Okay. But if you look at the heat sink temperature rises here, when you have forced air, those are considerably lower than natural convection, right? So a fan would allow higher power to be dissipated by this heat sink without exceeding the maximum junction temperature. Okay, so this is a basic analysis. If I were putting a few amps through a MOSFET, right, I would do this analysis. You know, if I'm doing more than an amp, if I'm using more than an amp through a MOSFET, I'm controlling it, I'd think, do I have to hook this to the case? By that, I mean the product case or the prototype case. Do I have to use a heat sink? Do I need a fan? So you would go through this analysis just to get an idea, are you close to the limits? If you're not close to the limits, I'd probably stop here after a sanity check, maybe a measurement. And then if you're really close to the limits, then you really have to go into some more detailed thermal analysis, get your thermal engineer involved using some better modeling tools. Okay. But I guess a point also I want to make here is the electrical design choices affect your life as a mechanical engineer or other engineering disciplines, right? If you were right on the border of this working, maybe just over the border, so you think it wouldn't work, then you might ask the question, well, wait a minute, look at this 67 milliohms right here. Wasn't there a way to get that lower by using a higher gate voltage? So could the electrical engineer use a higher gate voltage somehow and drop this resistance and get you below a maximum junction temperature? So when you have some knowledge of electronics, in this case, MOSFETs, and some of the details about MOSFETs, when you have that knowledge, you can start questioning, well, wait a minute, there might be a way to get around a tough mechanical challenge so you don't exceed your swap C requirements by adjusting something simply in the electrical domain. Okay, so that's the power of looking a little bit across disciplines. All right. Okay, so that's my thermal discussion and my heat flow discussion. I want to finish up MOSFETs with a couple more details and things you've seen in lab. We talked about a little bit in lab, but now that you have some MOSFET background, you might be able to put this in context just a little better. Okay, so the MOSFET circuits often have these two resistors connected to the gate terminal. So you saw this in your lab project schematic. You have this R sub G gate resistance and this R sub pull down. It's a pull down resistor. Okay, so that series gate resistor is for this purpose. That gate to source interface appears as a capacitor. Remember, the gate to source is isolated by a dielectric, an insulator there. So that means you have essentially a capacitor in this device unintentionally. And for a capacitor, I of T is C dVdt. So the current through that capacitor, in this case, the current into the gate is C dVdt. And you say, well, wait a minute, I thought gates are insulated. You can't have any current going into the gate. Well, that's for DC, or when you turn DC on. But if you have a capacitor, a current cannot go through a capacitor, but that capacitor charges and discharges. So the current is the charge either accumulating in that capacitor or discharging from that capacitor. And that's described by I equals C dVdt. Okay, so without the gate resistor, you could have a sharp edge of the control voltage, like that which comes out of your microcontroller, some kind of sharp square wave. So you could have this sharp edge, this very steep slope dVdt, and that would cause a large, very short duration, but a large current from the control voltage source, like a microcontroller or other digital integrated circuit. So the gate resistor limits that maximum current, okay, which is generally good. You could damage a device if you try to get too much current out of it. You might cause electromagnetic interference problems. You might cause power supply droop. So if your application can tolerate it, you want to limit that slope. Okay, and so VGS is actually going to show an exponential change. You have this RC time constant. So while limiting current, you've got this RC response, resistor capacitor response of VGS. Okay, so what's that going to do? That's going to cause the gate voltage to not either be low or high, but have some duration in between. Right, so you're going to have a longer stay in the saturation region. And remember, when you're in that saturation region, you have simultaneously non-zero voltage and non-zero current, and that means power dissipation. So this resistance can cause higher power dissipation in the MOSFET, which brings you back to the thermal problem, right? Okay, so that's what the gate resistor is typically for. Then there's this gate pull-down resistor, or pull-down, or whatever it's named. So the pull-down resistor brings VGS to 0 volts if the control voltage is removed, or if, for example, the microcontroller output port goes to a high impedance state, which means basically open or almost open. Right. So if your control voltage is either applied or open, when the open is presented after maybe 5 volts was presented, you have a charge on VGS, and if you just disconnect the control voltage to high impedance, without this pull-down resistor, the MOSFET can just stay on, and you don't want that typically. So this pull-down resistor brings that gate low. It's a connection to ground through that resistance. If you don't have that, the MOSFET could remain in a conducting state, which is typically what you don't want when you want a device to turn off. And notice how this pull-down resistance is to the left of RG, not on the right of RG. You know, a resistance on the right side here would also pull down the gate, but then what you're doing is you're forming a voltage divider between RG and R pull down if it were on the right. So you have a voltage divider, and now your control voltage isn't applied directly to the gate, it's applied through a voltage divider. It's going to be potentially lower. All right. So those are those two resistors. You'll see that. So when you're designing your robotics project, you're just turning on a motor, right? You're designing your robotics project or motor project, or, electric bike project. Consider putting these in there. And if you get some odd behavior of your MOSFET switching, consider putting these in there. All right. All right, let's talk about a couple other considerations. So let's talk about MOSFETs when you use them with DC motors or really any kind of inductive device like a solenoid, a relay. You might be using a MOSFET to drive a solenoid that takes higher current, or a MOSFET to drive a relay that requires higher current through the coil for the relay to control even higher current. We're going to use a diode there, what we often call a flyback diode. So DC motors are inductive loads. They have coils in them, and that forms an inductor. They're magnetic devices. So for an inductor, we know that the voltage across an inductance is L times the derivative of current. So if current changes fast, then that causes a large voltage. So if you have some kind of rapid shutoff of current, you're going to get this big voltage. Well, that rapid shutoff could be your MOSFET turning off the current. Right? So when you're applying a pulse width modulated signal, you're turning the current on and off rapidly. That means you could get very large voltages. So the high voltage spike across the motor caused by that change in current could damage the MOSFET, and it could damage other devices connected to the circuit. Okay. And so if you shut off this current really fast, the motor current really fast, right, a very steep slope, that means a large DIDT, then you're going to get a big negative voltage, a big negative V motor here. Because if you shut off current, that's going from, let's say an amp to 0, that's a negative derivative, you get a big negative voltage. And we need something to dissipate the energy stored in the coils and suppress that high voltage spike. It might be very short in duration, but it's going to be there. So what we do is we put a normally reverse bias diode right here across the motor or across the solenoid or across the relay coil. Okay. And so when the inductance of the motor tries to create this big negative high voltage spike, you're going to have this diode conduct. So when the motor's running and you have a positive V motor across the motor and the diode does not conduct any current. It's reverse biased. But when that motor voltage tries to go negative, more than the forward voltage of that diode, then current flows through that diode. That diode actually dissipates that energy stored in the motor. Okay. And often a diode called a Schottky diode is used versus just a regular silicon general purpose PN diode. And that's because the Schottky diode has a lower forward voltage. So it starts conducting at a lower voltage, more closer to 0.2 volts compared to 0.7 volts. Okay. So you will see a lot of names on the internet and textbooks and different applications. It really depends where you're reading about this diode, but you'll see this called a flyback diode, a voltage snubber diode, a commutating diode, a freewheeling diode, a suppressor diode, a clamp diode, or a catch diode. So any one of those is probably referring to a normally reverse biased diode protecting a circuit from high voltage spikes. Okay. All right. So for MOSFETs, we covered what they are. We covered the characteristic curves, how to apply those characteristic curves. We talked about different examples. We talked about thermal analysis of a MOSFET, how you might get the heat out, and then these details that might save your circuit, like this flyback diode. So we're going to next talk about DC voltage conversion and DC voltage regulation. And one of those topics, voltage conversion, will actually apply MOSFETs. So you have to talk about MOSFETs before talking about DC to DC conversion. But this all falls under this topic of power sources and control. So we talked about batteries, those are the sources. We talked about MOSFETs, control on-off, control pulse width modulation. Now we're going to talk about DC voltage conversion and DC voltage regulation. So you typically use DC voltage conversion and DC voltage regulation to power a load using a source that has a different voltage. Okay, so here's a source that you want to connect to a load, and the source voltage is different than the load voltage. There could be various reasons for that. Maybe you have an existing power supply that is different from the load voltage. You might have a battery that doesn't match the load voltage. Or you might have a battery that discharges, and as that battery discharges, the voltage falls, and you want to maintain a constant load voltage. So various reasons why you want to use DC voltage conversion in the middle here. Okay. So DC conversion usually refers to a change from a nominal source voltage to a lower or higher nominal load voltage. So contrasting with regulation. So conversion is usually you go from a source voltage to a load voltage, and the load voltage could be either higher or lower than the source voltage. We'll talk about circuits that do that. So you might have a 9-volt battery powering a 5-volt circuit board. So you have to step down in voltage. Or you may have a 3-volt battery powering a 5-volt circuit board. You have to step up in voltage. Okay, so that's what this conversion does. So regulation, DC regulation, often refers to the function of maintaining a constant load voltage, even if the source voltage changes or the load current changes. Okay, so you want to maintain a load voltage if the source changes. Now, AC conversion, I'm sure you've seen transformers on power poles and transformers in some devices. AC voltage conversion is different. It can be performed with a transformer with a different number of turns on each coil that are magnetically coupled together. Okay, so just a turns ratio can transform a sinusoid from, 5 volts to 20 volts or 120 volts down to 12 volts. But that requires an AC waveform because the way you induce, you take a primary coil, you create a magnetic field that induces a voltage on a secondary coil, and you have to have a time-varying magnetic field, time-varying current, time-varying voltage to do that. So DC voltage conversion requires a more complicated circuit with switching and or feedback control compared to a transformer. A transformer is a couple coils of wire at least around a core. But DC voltage conversion requires a circuit that has usually switching and feedback control. So the DC to DC converter that you have in lab looks like this. So that's more than just a coil, a couple coils of wire. And you can choose DC conversion approach based on, you can choose the DC conversion approach based on the requirements of what kind of power efficiency do you need? Does your approach of converting voltages have to be really low noise? Do you have to use a single component, or can you use a circuit board based on your swap C requirement, size, weight, power, and cost? So here are DC conversion approaches. So here's a linear regulator. This is a single integrated circuit on a surface mount package, in a surface mount package. These linear regulators, and we're going to show an example, we're going to talk about an example, they use what's called a pass element to cause a voltage drop between the source and the load. And because they cause a voltage drop and they have current through them, they dissipate power, and they can have poor power efficiency. They can cause poor power efficiency if you have a large difference between the source and the load voltages. So that's a downside, but the upside is typically they're low noise and they're small size. Now, switcher converters, DC to DC converters, they rapidly switch a pass element, and then they use an inductor and or a capacitor, typically both, to decrease or increase the voltage and provide filtering. These typically have good power efficiency because they're using switching, which I'll show you, versus using a voltage drop across the pass element. So that's good. They're more efficient. The downside is they're typically larger in size, right? This is larger than a single surface mount component. And they're more complicated. So that affects size, weight, power, cost, reliability, all that good stuff. Okay. So we're going to dig into these approaches. I'll show you how they work. I'll show you applications, and we'll start that next time. Okay, but I've hit the wall on time. So in closing, check Canvas for the upcoming due dates and due times. You'll see you have a homework due this week. If you have any questions, you want to talk about anything about the material, or anything, stop by office hours. I will start those in just a few seconds. And so if you'd like to join, please join. If not, I'll see you next time. Have a great night.